Hey kiddos, today we are going to talk about mass spectrometry. Mass spectrometry is one of a bunch of different techniques that as chemists, or really scientists, we use to properly identify what molecules are, whether they're just single atoms and we're trying to find isotopes, which is sort of the stuff that we'll talk about today, or whether it's sort of like you're watching CSI and they pop the stuff in the machine and it spits out an answer. Of course, it doesn't work quite that easily. There's a variety of different techniques that would have to be done, and it certainly wouldn't be done in a 12-minute span or whatever. But a mass spectrometer, which is what we're going to go over today, is one of those devices that would get used. It would get used along with infrared spectrometry and some ultraviolet work, some nuclear magnetic resonance, and some gas chromatography and some HPLC and all of those sorts of things together. So we're going to talk a little bit about mass spec here, and then in our next video we will talk a little bit about the outputs of mass spec and how we would use that for some calculations in a chemistry class. So mass spec, here's how it works. Essentially, they're all going to come down to basically the same thing, and there's all kinds of varieties of them. They work in slightly different ways, but essentially it comes down to this. You've got a tube. You've got an input going in one end. We're going to get an output down here, and I'm going to briefly walk you through the parts of how do we get to that. Really important applications. This was actually one of the first things that the Y12 plant up at Oak Ridge did, was that they were separating uranium. Uranium-238 is what most uranium is. Okay, if we pull it out of the earth, it's 99% or so of U-238. But what they needed for the weapons programs for the Manhattan Project was uranium-235. And so at the beginning of the Y12 plant, what they used is what were called calutrons, which essentially were separating things by this same general principle that we're doing with the mass spec. So let's talk about what's going on here. So in this end, we have what is called the input. Now the input, typically speaking, it's going to vaporize the material to turn it into gas phase. That's sort of essential for the next step that's going to go on. This makes it really easy to pair up with a gas chromatograph. It's called a GCMS, so a gas chromatograph mass spec would go through this thing together. So you do the gas chromatography first, split the things apart, and then run it through the mass spec. Anyway, we're going to vaporize it, volatilize it. And then the next step is what's really important. This is step one of what's important about making it a mass spec. And this is what's called the ionization chamber. Okay, so what's going on in the ionization chamber is exactly what it sounds like. Ionization is occurring. So there's beams of high energy electrons coming through here. So our input, our sample is this dashed line going through here. It's going to get beams of high energy electrons hitting it, and what those high energy electrons are going to do is they're going to knock off other electrons. They're going to give what's left a positive charge. So we've got a beam of our material, or a stream of our material going through here, and what was once probably not charged now has positive charges. So the ionization chamber is going to give everything a positive charge. So once it has the positive charge, it's then going to get pulled through. And if you're wondering, like, why would it keep going? Why doesn't it just sort of hang out in the ionization chamber? Well, obviously, there's some pressure considerations and all that too. But what's going on here is that there are magnets. Specifically, there are accelerating magnets. They're going to pull it through. So essentially, they're getting built up with a negative charge. Since our sample that we put in has a positive charge, it's going to get pulled towards it, and some of it is going to go through these slits in the middle, these holes in the middle. Now, as you see, it should be going on a straight line path, which would mean that it should hit up here. We don't want it to hit up here, though, because our detector's down here. And so what's going on in the next part is that we have our deflecting magnets. That's an F even if it doesn't look like it. Those deflecting magnets are going to do, again, just what they say. And they're going to deflect the path of those electrons. So inertia would say that, hey, if nothing acts on them, they're going to keep going that way, right? So the deflecting magnets are going to essentially alter their path so that they're going to come down this way. And they're going to strike the detector. And the detector is going to read and say, hey, how much of this stuff do I get? What's the intensity of the signal that I'm getting at these certain places? Now, certain places, what does that mean? Well, here's the real important part behind a mass spec. Why is it called a mass spec? We haven't talked about mass yet. Well, remember that I said that if we were putting this in and say we had U-238, okay, that's the most abundant isotope, but what we really wanted was U-235. Okay, so how do those things get separated? Well, it's simple physics, because the deflecting magnet is working on them, and as you have isotopes or particles or whatever in a mass spec, but in our case we're talking about isotopes, that have a different mass, well, a heavier mass, the U-238, is going to get deflected much less than the U-235 is. So while this beam, the initial one that I have here, might be the U-235, the U-238 doesn't have its path bent quite as much, and so it's going to hit the deflector plate further out because bigger mass, more inertia, it's not going to get its path altered quite as much by the same amount of force. This is essentially how all mass specs work, and what we're going to read out, and what we'll see a little bit more of in the next video, is we're going to get a readout that essentially is going to be a graph, and on the y-axis here it's going to be intensity, okay, and on the x-axis essentially what we're going to get is we're going to get what's called an m/z ratio, or a mass to charge ratio. Okay. Now in theory we've got mostly the same charges coming out of the ionization chamber here, and not all. They're going to be broken up a little bit, but if we wanted everything to look pretty, we'd assume that they all ended up with the same charge, and then we get a mass. And so, like in our case here, let's say that this was 238, maybe over here is 235. I'd get a really big signal at the 238 part. Okay, let me carry this graph out a little bit. I get a really big signal at the 238, and yet at the 235 I would get a much smaller signal because it was about 1% or so, whereas the 238 was about 99%. That's going to lead us to things like relative abundance, and is going to allow us to do some calculations of what actual atomic masses are. Okay? So that's how a mass spec works in general. Obviously, you can go into a lot more detail and research a lot further. I highly recommend looking at the Royal Society's video on mass spec, because they're going to talk a little bit about the theory, but they're actually going to show you how it works on a real machine. I think that's pretty cool. Okay, so thanks a lot, kiddos.